So we'll walk through a use of some of these exponentials. Here's our formula, a times b to the x. We're not going to worry about k here. What a is going to be for us is the initial value, and that'll make a lot more sense in just a minute. And then b is either the growth or decay rate. And this is going to come back to what we were doing before when we were talking about increasing versus decreasing. So growth happens with those graphs that were increasing, and decay for those that are decreasing. There's going to be a trick that we play with some of these. If b is bigger than 1, that's when we had that increasing graph, which means we had growth. So if b was between 0 and 1, basically some kind of fraction or decimal, not bigger than 1, that's when you have decay. So to find the growth factor, you do 1 plus the rate, and to find the decay factor, you do 1 minus the rate. So that's going to make a lot more sense if we think about it in some examples here. So the world population was 2000. In 2000 was about 6.08 billion. The annual rate of increase was about 1.26. So the growth factor, which we're calling B, is 1 plus the rate. Now what we want to do, we want to turn that percentage into a decimal. So that's 0.126, right? So 1.26, change that to a decimal, 0.0126, because we have to move the decimal 2 places, right? So our growth rate is 1.0126. So the function to model the growth, right? A is the initial value. Well, what was the initial value in 2000? It was 6.08 billion. And then the growth rate was 1.0126. We just raise that to the x power. A computer depreciates in value, so it's going down, it's decreasing at a rate of 14.3% per year. So first thing I want to do, 14.3% as a decimal is 0.143. So the decay rate, and if we go back up to the top, decay rate, we do 1 minus r. So 1 minus 0.143, and that is equal to 0.857. So again, we can write the function that models the value of the computer. So the initial value was 6,500 times the growth rate or decay rate, and here's decay rate, 0.857 to the x. What we end up wanting to do with some of these, here's an application. Let's find the value after 3 years. So in other words, we're going to use this function, y equals 6,500 times 0.857x. We're going to plug in x equals 3. So this is we're not going to do this by hand. Go to your calculator. What we're going to do is we have our 6,500, and then we have, we'll put our parentheses, excuse me, our parentheses, 0.875, oh, excuse me, 857. I'm going to raise that to the third power for the third year. So what that tells us, the calculator, excuse me, the computer, right, 6,500 0.857 to the third power is worth, I already forgot, 4,091. And since it's money, when I round to 2 decimal places, 0.25. So the population of a species decreases at a rate of 1.35. So this is going to be 1 minus r. So find the initial value. So a here, the initial value is 80, right? You've counted 80. The b equals 1 minus the rate. So again, 3.5, change that to a decimal, is 0.035. So we got to do 1 minus 0.035, and that is 0.965. So our function that models that, a 0.965 to the x. So estimate the number of years it first drops below 15 animals. Here's a great use of Desmos, if you will. So take a moment, pause this, and open up a Desmos window. So here I've gone ahead and I've put this function into the calculator, but the initial graph we don't see anything. What we can think about is actually the past couple days we've realized that a value is also the y-intercept. So that should give us a hint that we're not zoomed out enough on this graph. So um, if we zoom out enough, there we start to see the graph. So what we want to try to do, right? So the y-intercept is the population, and this is number of years. So how long is it going to take to get to 15 animals, if you will? So let's just grab a point and start kind of working our way through it. Um, and work our way through. So here after 34 years, there's about 24 animals. After about 40 years, right, after about 40 years, there's 19 animals. So keep going until we get to 15. So it looks like at 47 years, we get 15 animals, right? So just grab a point and drag it along until you get the value you want. So for us, right, we were looking for when does y equal 15? And it took us, again, right, when did we get to 15 animals? It looks like we got there, I'm having trouble now, in 47 years. So in about 47 years. So it took a while to get there. But that's a great application of using your Desmos. All right. The value of an industrial machine decreases at 25% per year. So after 6 years, the machine is worth 7,500. What was the original value? So now all of a sudden, a little bit different look at this. So 7,500 equals, we don't know A, um, but we do know the value decreases. So B equals 1 minus 0.25. So 0.75 is your B value. That's 0.75 raised to the X. And we know that it took us 6 years to get here. So we're going to have to kind of think through how is it that we're going to get to this particular answer. So what we need to notice is that we've been plugging the number of years in for x, which is exactly what we're going to do here. So in other words, this tells us x equals 6. And it's at this point that we can just kind of solve this thing like a normal problem. So we have a, take 0.75 and raise it to the 6th power, right? So we have 0.75 to the 6th equals 0.17797. And what we need to do now, if we look back over here, so this was about 0.17798. But what we're going to end up doing is divide by 0.17798, divide both sides by that value. Or if you've got one of these graphing calculators, we can do 7,500 divided by, you can actually pull your previous answer by using that second answer function. And there's our final answer. So we'll call it 42,140. We'll just round to the nearest one, so that's 0.9. So 42,140. So the initial value was 42,140. Right? And that makes sense. If we think about it, if the value is decreased, it should have been worth a lot more than its current value of 7,500. So the function here models the intensity of sunlight beneath the surface of the ocean. So y represents the percent of surface sunlight at a depth of x feet. So the model is accurate from about 20 feet to 600 feet. So find the percent of sunlight 50 feet beneath the surface of the ocean. So in other words, they give us an x. So let's plug in x equals 50. So here, again, we're looking for y equals 20 times 0.975 raised to the 50th power. Just go to your calculator. Um, I'm not asking you to do that by hand. So 20, let's clear all this out. So we have 20 times point, make sure I get the right decimal in there, 0.975. We're going to raise that to the 50th power and hit enter. So 5.64, whatever that particular value is, 6.4 percent of sunlight. So we'll just put our context with that as well. Find the percent of sunlight at 370 feet. So again, we're just plugging in now x equals 370. So look back at the problem and it'll tell you what variable goes with these numbers. So y equals 20 times 0.975 raised to the 370th power. So it's just a matter of plug and chug here, guys. So 20 times 0.975. I'm going to raise that to the 370th power. 0.0017. So 0.0017% of sunlight. You think about that for just a minute. Context says if you're 370 feet below the surface of the ocean, there's not much light down there. In fact, it's almost zero. So take a moment, work through page 14 now on your own, and the next video will walk you through how to solve those.